we have Tim Canham of NASA JPL presenting the Ingenuity Mars Helicopter Operations Overview. Tim, it's all yours.
Well, thank you, and good afternoon, everyone. So just for those of you who don't know who I am, my name is Tim Canham. I am the flight software and operations lead for the Mars Ingenuity helicopter. So early in the project, I was leading the team to develop the software. And then as we transitioned to operations after we delivered the helicopter, then I led the operations team where we designed the process and the tools for doing the operation helicopter itself. So next. So we'll look at these different topics in this presentation. We'll talk about the helicopter as a project. We'll look at the hardware for the helicopter. We'll look at a software description. Then we'll talk about operations, how well it performed, some of the anomalies that we saw, and software updates that we plan, and then a nice little infographic at the end. So next slide. So what is the helicopter project? It's a class of project for NASA. They call it technology demonstrator, which is something that is not a full up, what they call Class B project, where everything is rad hard and super tested and using established space technology. But instead, the project is free to pick things that are a little more bleeding edge or a little more off the shelf in order to try something completely new. And obviously a helicopter on Mars is something completely new. And we were paired with the Perseverance rover, and we landed there in February of 2021. So almost a year ago now, the rover landed. And we originally slated for 30 sols, which is the term for a Martian day. And then we would be done. And that ended up happening in April of 2021. So the rover did its own checkout and commissioning, and then moved to a spot which actually ended up being very close to the landing site in order to do the helicopter phase of the project. And then we had originally allocated 30 Martian days to do all of our test flights. But at the end of those 30 sols, the helicopter was still in tip-top shape and working really well. So they decided to extend our mission, and we're still doing it. It's these slides are as of early January 2022. And we actually did complete a flight yesterday. So we downlinked the data, and the helicopter completed flight number 19 just yesterday. And what's the purpose of this project? The purpose is to gather detailed flight performance on Mars about how the helicopter behaved in order to inform future missions, which could use rotorcraft like this to do other aspects of Mars exploration. And so the initial purpose was just get this flood of data from the flights so that we can have this historical record of how well the helicopter performed. But in the extended mission, we expanded to do sort of a notional scouting for the Perseverance rover. Now, they don't need us. We're not a critical part of the mission. We aren't essential to completing their mission, but it gave us a chance to sort of practice doing scouting, which would be one of the possible future uses of the helicopter. So you can see some nice pictures here. You see the picture on the lower left of Ingenuity just after it was dropped on the surface. And then you can see flight, I believe it was number 4 flight number 3 as it went to the north and returned. And on the lower right, you can see an animation of the navigation, the black and white camera as it pointed down during the flights. And what was a big surprise to all of us is kind of the frozen blades image, which was kind of a cool but unanticipated way that the camera imaging manifested itself. So there's some nice pictures. So next slide. So here's a good idea of how the scouting concept has fleshed its way out. Is the rover and the helicopter have been scouting what's called the CETA region, which is a kind of a rough depression, triangular shaped depression to the southwest of where the rover landed. And it's very rocky. It's got kind of dunes. It's got some sloped areas. And so the rover will only go into CETA with a certain amount of care because they want to make sure that they don't get hung up on any rocks or they get caught on a slope or get stranded in a dune. So what Ingenuity has been doing has been scouting that area for the rover. And you can see some examples like in the lower left, there's a picture where you see the the image from orbit is kind of grainy. It's not very well defined. But then as Ingenuity flew over that region, you can see in that more gray section how the more detailed pictures from Ingenuity were able to fill in what they could see only more vaguely from orbit. The middle picture is a case where we actually went into CTOB, and the helicopter has a 13 megapixel color camera that's kind of pointed towards the horizon. And so as it flew, it was taking pictures, and you can see that kind of orangish rust colored area where, again, the gray area is the rougher orbital images, and the helicopter's color camera was able to fill in greater detail as it flew of that region, and see with greater detail some of the features. And on the right was an actual case where you can see there's one of the color pictures that was taken while we were aloft, and as an ode to Dr. Vertesi, you can see I'm making motions like I'm a helicopter. So there's a close-up image of an area that the rover was wanting to traverse, and based on images that we gave them, they were able to pick what was probably a safer path to their destination based on the images that we sent. So next slide. So let's take a look at the helicopter system itself. So the helicopter system really consists of two units. You can see on the left there the base station, which is actually an instrument payload on the rover itself, which they've nicknamed Percy by this point. And that acts as an interface between the helicopter and the rover. So it has contained inside of it a radio, which is based on a Zigbee radio. We modified the firmware to make it more suitable for how we wanted to use it, but at its core, it's really a Zigbee radio, the kind of radio that's commonly used for, home automation. And the base station would interface with the rover. And so during a typical flight, we power up the base station, the helicopter wakes up, we talk to it, we pass it commands, etc. And then the data gets sent back to the base station. And then at some point after that, it gets transferred to Percy and then to the ground. We'll show a little schematic of that later, a little picture. On the right, you can see the helicopter electronics. It's a cube avionics in the shape of a cube that goes inside that thermal blanket you can see between the legs. And the helicopter electronics and the base station electronics share a lot of common boards. They're just packaged differently. The FPGA is a little differently coded up, but they share a lot of avionics. And so we'll dive into that a little bit if you want to switch to the next slide. So here's kind of a block diagram of the different parts of the helicopter. We're leaving the base station aside for now. We're looking at a block diagram of the helicopter. So the helicopter has really two processors at the core of how it operates. There's the Qualcomm Snapdragon 801. You can see it in the picture up there in the form it came as a kit. We took the plastic off and we deconnectorized it and we wired up where the connectors used to be. And it came with a pair of cameras. You can see there on the left, the Sony has a Sony sensor, the 13 megapixel color, and then the OmniVision, it's a machine vision camera. It's black and white that points down towards the ground. You can see the Zigbee radio. There is a microsemi, a ProASIC FPGA that acts as the rad tolerant core of the system that has a lot of the things like motor control and sensor acquisition. There's a number of features, watchdogs. Those are in the FPGA that we had an FPGA designer that designed those features. And then we also had a TI microcontroller. It's an automotive grade microcontroller. It's dual core, an ARM R5 for those who know those families. These two cores could operate in lockstep, and then it can actually detect its own errors and signal an error. The Qualcomm Snapdragon ran Linux. We basically took the Linux that came with the board and wrote our software for it. Whereas the TI microcontroller is bare metal. There's no RTOS on there. It just runs a cycle at 500 hertz. And the software just executes that cycle. Whereas the software on the Snapdragon is a Linux application, multi-threaded application with messaging back and forth and so on. So we had a series of COTS, if you will, hardware for our guidance sensors. You can see there's a LiDAR, a laser rangefinder from Garmin that we put that gives us the distance to the ground. There's a Bosch IMU that gives us our gyroscopic motion, and then there's an inclinometer, which is really kind of a slow speed gyroscope that gives us our initial attitude as we're sitting on the ground. So all these sensors work together, and then the FPGA itself has what we call our inner loop motor controller, which does commutation of all the different motors that are part of the helicopter. And the software on the TI microcontroller commands that FPGA in an outer loop motor control to keep the helicopter aloft. Next slide. So the helicopter application, again, to zoom in there, you can see on the right, we have a little block, kind of a high-level block diagram of the different modules. It uses the F prime open source framework, and I put in there a link to the GitHub repo. It's an open source framework. Now, obviously, the helicopter software itself is custom and internal to JPL for IP reasons, but the framework itself was available for anybody to download and try out. It's a component-based architecture. You can think of them as building blocks like Legos that plug together and interact via these connections. We reused a lot of code from previous missions that we've flown that have flown F prime, and indeed it actually shares code internally. We don't show the block diagram for the base station, but many of those green modules and purple modules that you see in that diagram were also on the base station, so we're able to get a lot of reuse out of it. And also the component architecture, because it was so plug and play, it allowed us to put together a bunch of different combinations for different testing environments, different development environments. For instance, we had a little mini deployment that we sent off to the telecom team, so they were able to develop on a Raspberry Pi for many months before they actually met the helicopter hardware. So I gave more details about 2.5 years ago, the last time we met in person for the flight software workshop. I gave a presentation there goes into more detail about the software. And so if you'd like to, you can click through that link and take a look at that presentation. But you can see here that we have this partitioning between the two software sets that are on the helicopter. The Texas Instruments on the bottom, where we did, because it was bare metal, we developed a set of components to run within there and talk to the different guidance sensors and the motor controllers and everything. And then on the top, where you see the green modules, those were ones that we inherited from previous projects that are the ones in green are actually part of the open source distribution if anybody wanted to use them. And then we had some custom ones for the helicopter. So next slide. So what's the concept of operations? So it's important to understand how the rover itself works, because we had to work through the rover. So the rover's not in contact directly with the Earth all the time. Its activities are centered on a Martian day. So in the morning, basically the Martian day, the team on Earth will uplink a series of sequences to the rover. So you can advance to the next animation. You can see little files go from the Earth to the rover. And then typically after that's done, since it's one way, they get tones back to say, yeah, we got everything. But then the rover operates on its own all during the day. And because the conditions are best around noon Mars time, that's when we do our flights. So you can hit the animation button again. So the helicopter will take off and do its flight and then come back and land. And once we're complete, then we do a transfer to the rover of all the data from the flight. So you can hit the animation again. You can see we send like a picture back to the rover. That's many other things, but that's a little animation to show you. The idea is that we transfer them back to the rover. And then what happens is later in the afternoon on the Martian day, they'll get overpasses of spacecraft like MRO shown there. And the data, because the data is much higher volume, there's a UHF link between the rover and the orbiting spacecraft. And then that, in essence, relays it back to Earth. If you want to hit the next animation, you can see the picture that we got from the flight gets relayed back to Earth to the ground team. So there really is no live coverage of the flights. So the helicopter is doing its thing without anybody watching. And there's no live coverage of a flight. And so once we get back all that data to Earth, then that's when the ground team gets involved. So next slide. So what is operations on the uplink side? And many of you who've participated in flight projects is a very familiar cadence here. is that our team writes sequences for the rover, and then for the base station and the helicopter, because they're really the three computers that are acting on commands. And we've developed a set of tools because there are time-dependent parts of those sequences, like telling when the helicopter when to wake up, when to turn heaters on and off. So we've generated a set of Python tools on the ground that can take the human error out of that by using some standard time libraries that JPL provides. And then for a given day on a given flight, the guidance navigation control team will give us specific commands to insert into our sequences to actually do the flight. So we have these general boilerplates, if you will, of sequences that surround the flight portion, and then the GNC gives us a little snippet that we put in the middle of the sequence to actually execute the flight. Our ground team also wrote a set of linters that we can use to scan the sequences to make sure there's not some common errors like file misspellings or missing statements that are kind of important, because the sequencer will just compile it, but we want to make sure we're not missing anything. Once that activity is done, we basically transfer our bundle of sequence to the rover team, and they include it in a big parcel that they upload at the beginning of the sol that I showed you in the previous slide. So we're working very much hand in hand with the rover team to supply them the sequences they need to execute the flight. So next slide. So on the downlink side, you can see here a nice picture from the first flight. So we developed another set of tools that would process the helicopter data as it comes down. So again, we wrote a series of Python scripts to automate the process. If any of you saw the live landing video, you could see all those tools operating in the background. As you can see in the picture there, Michael Starch, our downlink lead, you can see the monitor in the middle that's running all of our downlink tools. They go out to where all the rover data is stored that got downlinked via that relay I mentioned, pulls them all out and decodes our specific data products, and then pushes all the data to an Elasticsearch instance that we have at JPL. Once it's all on the Elasticsearch, then we run a series of reports and analysis to figure out, what happened. So we look for errors, we do analysis. You can see the plots and the pictures that are generated as part of that. We have these highly detailed logs. The guidance, the GNC loop runs at about 500 hertz on the helicopter, and we're taking data every cycle and dumping it into data buffers, which end up going into a file after the flight. And we give those big logs to the GNC team, and they run their own analysis tools to figure out exactly what happened. An example of that is that plot there next to the picture. And the navigation images, the navigation being the downward pointing black and white camera, we take those as we're landing, and those last couple of pictures are used to localize where the helicopter actually landed, because there's a little bit of error in the guidance algorithms, but we're able to pinpoint once we land where we actually landed. So next slide. So how did the software do? Software, as I mentioned, it's running at a really high loop rate compared to the rover. The rover during EDL does 64 hertz guidance. Ours does 500 hertz on the GNC loop. Also does a feature tracking loop at 30 hertz. You can see sort of a depiction of that on the right, where we took some of the navigation black and white pictures, and we superimposed on them the points that the feature tracking algorithms found in the image and how they migrated from frame to frame. It's part of how we do our navigation. So the big challenge here was we had to do all this testing piecewise on Earth, because we can't fly in representative gravity and representative landscapes. So we did a series of these tests that we did, and then they finally came together on Mars. So as you can imagine, we were holding our breath during the first few flights, having all this stuff play together. Next slide. So software people like to see plots. Here's a plot of the CPU utilization. The Snapdragon is a quad core processor. You can see on the right what each core was kind of given as a job to do. You can see during the flight, the GNC cores were busy doing their thing, doing their tracking, but you can see that the Snapdragon is powerful enough that it really wasn't getting pushed too hard to the limit. We're running, during a flight, we're running at about 40 to 50% utilization. Once we're done, then we go into a lower power mode and we start to dump all the logs to storage. So we have a ton of these logs in RAM, because we don't want to write to the file system during the flight, because sometimes there can be latencies in the kernel that can cause interruptions. So we basically push all the data in memory, we write it to storage, and And then as kind of a thing that we figured out later in the project was we can take those files, because those files can be large, and we can actually run a Linux utility, bzip2, for those of you who know what that is. We can actually compress the files, and then later when we send them, they go over the radio and the rover link to the Earth much more quickly. And so you can see these different phases of the flight and how it affected our processor performance. So next. So what about anomalies? We had a couple of fun anomalies. We had this first one was sort of our Apollo 13 moment. Some of you may have read about it, but before we even got to our first flight, we discovered an FPGA bug that we hadn't exposed on Earth during our own testing, is that the watchdog was looking for a specific pattern to stroke the watchdog. And the software, because it was dependent on the boot time, when it was on Earth, it was booting slightly different so that it would stroke the watchdog correctly. So that the watchdog had an advertised function, but it had a bug where it had to see the right pattern at an exact time rather than any pattern to start it. And so we were on the surface, and every time we would boot, the watchdog would expire. And we were trying to figure out what to do about it. I was involved pretty deeply in that. I spent 2 or 3 days just buried in FPGA design, software design with the FPGA developer to trying to figure a way around it. And we figured out 2 fixes. One was we already had test commands in the software that we could use to poke and prod various FPGA registers for test purposes. But we left all that on the vehicle. We didn't take it out when we flew. So we figured out that if we poked the FPGA in a certain way, we could get the watchdog circuit to reset, and it would work 85% of the time. And we actually did that. We used that to get through our primary mission. So we had a couple of flights that didn't work because we hit the 15%, and then we just reflew and they worked. But the final software fix was to basically send both patterns every cycle so that the watchdog logic would be happy. We ended up updating that, doing that fix partway through the summer, and that's now gone. We don't have to deal with it anymore. Next slide. So this one was another one that was a little scary, was that the navigation images, when we take a picture with the black and white camera, it sends a pulse to the FPGA, which time tags it. The time tag is sent back to the navigation processor and queued up so that the next image, that when the driver delivers the image, it's paired with the time tag. And that tells the GNC algorithms where in time the picture was taken. But we had this happen once where the driver took the picture, pulsed the FPGA, and then dropped the image. So the timestamp was waiting in the queue. The next image came along, and it took the top of the time tag off the top of the queue and matched it with an image that was actually later in time. And that really confused the guidance, the GNC algorithms downstream, because they were getting IMU data, but they were getting contradictory image data. So it's kind of like the eye is not being in synchronization with the ear canal. And so it caused, as the GNC team described it, dangerous oscillations in flight. And my more parochial term is it was flying around like a drunken sailor. You can see from this picture that we took during it, it was kind of weaving around a bit, but there was enough margin in the design and the robustness of the GNC software that it was able to kind of power through that and still land. And we did a
1 minute warning, Tim.
Thank you. The fix for that was that we basically did a sanity check on the time tag and threw out an image if it was way out of bounds. And we actually haven't seen the anomaly again, but we did that fix. So next slide. So software updates, we're actually getting close to doing those. We want to do some variable speeds per segment so that we can have, we can dwell longer in some places and transit faster. We're tweaking how our sequencer works to work around various things that we saw happen during the flight, where we can ignore commands that it's okay if they actually fail. Also timing out of certain commands. We're moving some operations to a different core on the processor so they don't risk tripping that watchdog. And we had some minor fixes to how we execute commands on the Linux shell. So next slide. So here's our final infographic, the last slide. You can see here that I've compiled this as of the first week in January, so these numbers have all gone up, but We've transferred about 100 or 1.25 gigabytes of data since the flight started. We've done, as of then, it was 18 flights, 3.5 kilometers, about 32 minutes of flight. We've been alive for 272 sols. All those numbers have gone up, of course. And the navigation camera, 55,000 and change images processed by the software, and we saved off about 2,000 of those. We've taken 115 color images, and the software itself between the helicopter and the base station was about 750 lines of code. So that is the end of the presentation.
All right, thank you so much, Tim. Unfortunately, we don't have any time for questions, but we'll move the questions that we have received on the Q&A. We'll move them over to the Slack. I know I've seen you on there already, so hopefully we can have some of the discussion over there. Thank you so much for your time this afternoon.